I'm going to talk about joint work, equidimensional isometries, which is joint work with Emanuele Spadaro and Laszlo Zachariudi Jr., both in Leipzig. So, what I'm interested are isometric maps, and in particular why this class of maps is in certain situations very big, so prevalent in a topological sense. So what is an isometric map? Basically you have an F from one metric space to the other metric space, xd to yd prime, and the naive idea would be simply that d prime fx fy equals to d xy for every xy. Well, and if there would be no other structure on the spaces x and y, there would be no point in having such maps, right? Because it would be just a tautological renaming of the space. There's of course the first important class of spaces you could be interested in. D and D prime, if they both come from a complete norm, then let's put it like this: the additional assumption that you need f of x equals y implies that f is essentially linear plus a shift. It's usually called affine. So I suppose that x and y are linear spaces now, right? That's a quite famous result by Marceau and Ulam. Valid in all dimensions, and I think it's far from being trivial. If you have an elementary proof, it's easy, of course, if the norm which gives me the d prime is strictly convex. Because then you get basically that f of x plus y over 2 has to be in the intersection of the two balls, of the two spheres, f of x here, f of y is here, and the two spheres intersect just in a single point, and so the f of x plus y over 2 must be symmetrically precisely there, and then you easily conclude you don't need even the assumption that you are on 2. Right, because you have this linearity induced. Of course, in general, you need this assumption if you just look at you look just at x goes to x 1/2 sine x in L infinity over R2. So this is clearly an isometry, but it's nowhere linear. What is more interesting, and I learned it just recently, so I wanted to mention it in this situation. Actually, there is a nice continuation of this result by Figuier, and then using this Goffard and late Nigel Kaufen, basically to prove the following version, improving upon this situation. If f goes from x into y and is an isometry in this very nice sense, isometry x separable in addition, we cannot conclude that f is linear, but we can conclude there exists a linear f which is an isometry. So which is not really excluded by the thing, and that's what usually people in Banach space are after. They know for some reasons that they have a nonlinear map and they want to find a linear one. Of course, if they could differentiate, it would be nice, but in general, you cannot differentiate space. It's just the add-on on what Bob said about embedding into L infinity. Right. What is more interesting for us, linear structure, is usually incomparable linear and nonlinear structure. They are usually incomparable. The easiest case, if you look at f, which maps as 1 into R2, let's say with the Euclidean norm. And of course, on S1, you have to use the inner metric. So there exists no such f isometric if the metric on S is given by the length of the arc between the 2 points. Is minimum of t minus s and 2 pi minus t minus s. Right, and the argument is in some sense simple. S1 is just 2 times the interval 0 pi in this metric sense. So if you apply to both parts of S1, the argument, you see of course that the point in the middle must go into the middle between the 2 images here, and so they must kind of, you cannot keep the map injective. So linearity is an obstacle, and even coming back by what Bob said, we know we can embed into L infinity classical sequence spaces. You can also prove easily there is no f which maps S1 into any Rn with the supremum norm isometrically. That's more like a little exercise. So you might get frustrated, or you might ask your favorite geometer, and the geometer would tell you, well, that's clear because somehow on the image of f, you do not look at an inner metric, but you look basically just at the metric which is directly induced from a linear space to a non-linear substructure. So the geometers tell us look at the inner metric induced on fx by this norm, or by the Euclidean distance. And then, of course, we have the identity as the map we're looking after. And the same thing can be done in the realm of Riemannian manifolds, right? The same if you look for f from a Riemannian manifold m dimensions to a Riemannian manifold of n dimensions. We basically want only that the f is that f is infinitesimally an isometry, and the rest is taken care of by the construction of an inner metric, right? It makes it basically globally, then isometric. If I just pitch these pieces together, or not pitch here, but basically integrate. There's quite a lot of them you want to put together. So this means the condition is now that the df of x, which goes from the tangent space of the manifold M in the point x into the tangent space at the point f of x of n, usually this dimension is not the same, is a linear isometry. For every x. That's the condition they would suggest. And I say the rest is done by the inner metric to make it globally an isometry. And of course, you immediately see one condition is that the dimension of the target has to be bigger or equal than the dimension of the first. But in principle, it's not clear that you really need a strictly bigger dimension here. So what I will call basically, just for notation, f is called the short map. That's more the slang that comes from the differential geometry. It's called short map. If and only if it has a contraction, if and only if it is a one Lipschitz map. The Lipschitz constant of f. The Lipschitz constant of f is less or equal than 1. And we want to look at the question, do such maps with this property, are they in some sense huge in the space of all contractions? And the condition which I have said here, this condition star, is of course in general not sufficient to make the map really an isometry. In the global sense, you have to avoid somehow, for instance, that the map would be non-injective. Right? If you come back to the same point, of course, nobody will force you to measure the distance with the strange arc. But we can say if f is 1 to 1, and on f of x, which is a strict subset in general of n, we use the induced metric. Then f will be a global isometry. So far so good. Maybe make it sure what I mean. F is a C1 function here. This is the problematic assumption we will face in a moment. And so what do I mean by inner metric? I talked about it a couple of times. Of course, the definition all of you have seen, I guess, but sometimes people still think about it differently. If I have a metric space and gamma is a continuous curve, then the length of gamma is just the supremum of all these distances, gamma ti minus 1, gamma t I. You go from 1 up to some k, and the only condition is that 0 is less or equal than t, 0 up to t. Come on, that's the length of the curve. And it should also well known that this is basically the integral over the whole space x of the multiplicity of the values with respect to the, let me call it Hausdorff measure. Can't pronounce the H as nice as Andrew. H. The H measure. Alright, so it's the Hausdorff measure with multiplicity, it's the length. Right. And there are two aspects of this. When is the metric inner? So D is an inner. Sometimes people call it geodesic. Sometimes they use these things for slightly different variants of the same idea. Is the inner metric if for every x and y there exists a geodesic, which means gamma connects the x to y, and the length of gamma is just the distance of the 2 points. And a known construction, if D is any compact metric, then I define by D hat x of y, x and y, just the infimum of all the lengths, all the gammas, which connect x to y, an inner metric. Of course, it might become infinity in this way. Right? So, if you try to do this on the von Koch curve, for instance, it's a connected space, but you would get infinity as the metric. And these curves are so important because it turns out that this condition is actually the same as preserving length of curves. And this turns out, we will show that or understand that this is the right condition which we try to generalize. So let me remind you last time, it's again S4. Anybody knows where's the same one? What? Same. There's no 4 there. Okay, so it's the same place like today. And if we have, I mean, the compactness is needed just to make the existence of the geodesic safe. Sure. And now it's easy to see again. If the f is in C1, then it fulfills the condition up there. So the derivatives being isometrics, if and only if the length of all curves is preserved. Right? And so from the preservation of length of one dimension, we will deduce the conservation of area, two-dimensional, three-dimensional, and so on. So that's basically the best condition, easiest condition you should look at, preserve the length of curves. And now let me look at the question, what is different with the relation between m and n is considered more closely. So, what about the relation of m and n? Of course, m has to be less or equal than n is necessary. The first and well understood case is m less than n. So people figured out, of course, if their general Riemannian manifold should be somehow embedded into Rn. The higher the dimension of the target is, the easier the job becomes. So if you are sufficiently high, twice 2n plus 5 or whatever it was, then you can even, and the original manifold is smooth enough, you can even make an analytic embedding. But that's much beyond what we want. This always allows C1 isometries. So the easiest case, I looked around, I saw some of this device I would have needed. Oh. I hope you could hear me anyhow. I couldn't find any of the things I would have needed. It's just I want to make sure also the young generation understands me. If you look at the case m equals 1, how do you find these isometries, right? So basically, as I said, the statement comes more precise in a moment. But what we want to show, isometries are prevalent or at least dense in the set of all short maps. So how can you do this? Suppose you have a map which maps the interval from 0 to 0, 3, let's say, whatever it is, identically to 0, 1. So this is the image, so to speak, this is the gamma here, and this is the f of gamma. And I want a map which is very close to f, but which preserves the length of the gamma. And the obvious solution is the one which the engineers used before the mobile was invented. It's the chord of the telephone, right? So you would basically do something like this. And you can compensate for any defect in length, and you can stay as close as you wish with the map in L infinity, right? So if you look at what is done really, so this one thing was the f, and the f tilde maps to the telephone cord. What really happens, we basically replace the derivative of the f in the point x is in some sense approximated by the average, the local average of derivatives of the f tilde. And the picture is like this. the F tilde will be a one Lipschitz map, so the gradient of the F tilde will be somewhere on this circle, and averaging it out, I can actually realize any slope inside here, right? So my original map is a Lipschitz map, one Lipschitz map, so it has a slope somewhere in this circle, and I can approximate it by taking some suitable average over the circle, and that's why the method is basically later called by Gromov convex integration. So you take the convex hull of the allowed gradient in order to get something which is basically the original map you want to approximate. Okay, so in the case m equals 2 or is bigger or equal than 2, this is the hard part. One has essentially the theorem which was proved by Nash and then strengthened by Kuiper, and that's basically the situation that n minus m is bigger or equal than 2. This was Nash, and then the case if it's just 1 was done by Kuiper. And it basically tells us again, the most striking example is the following. For every epsilon positive, there exists a map F from the unit sphere as a Riemannian metric, Riemannian manifold, into R3, which is isometry as C1. Isometry such that the image of the whole map is less than epsilon. Again, it's no problem if you do this in one dimension. You take this guy and now you can wrap it. You can make the image as small as you wish, keeping it isometry. Of course, if you try to do this with a two-dimensional object, you do well in this. You do well in this direction. Let's say you make it very small in this direction, but then you start having a problem if you start bending in the second direction. There are all these sophisticated reasons, and one of them says, if you look at the map more precisely, with alpha here, then, well, the alpha has to be less. I think 2/3 is now well established, and it's alpha bigger than, now I'm not sure, this is, I think it's a little bit moving, alpha less than 1/10 is possible. So you can get the maps better than just barely C1. But of course, for instance, if you would imagine that you ask for a C2 mapping, you could calculate the curvature of the image of S2, and you would find out, well, the too small set has a much too high curvature, so you cannot do this. So, as I said, on the alpha, the C1 alpha case, there was work by Borisov, which was well announced and floating around for, well, I think 30 years at least, 40, 35 years, and then also Conti, Delelis, and Segali. Segalini looked in the thing once more, and they really established the bounds which I talk about. This position. I think at least the 1 over 10 is more comprehensible from their work. So there is the problem. Of course, we might try to find the right alpha. What you can say in general, if you just look at the C1 maps, then the isometries are dense in C1 intersected with Lipschitz one function, right? And here the problem comes up a little bit. In the moment we are not really able to give it a decent reformulation in the framework of the residuality, of topological residuality, talking about the bare category. It's not clear in which space it is residual. For the obvious reason, I mean, if f is just a Lipschitz one function in C1 and G is an isometry, then it's of course f minus G can be closed in the L infinity norm for the very simple reason, just a bit elaborated substantially. This is very small, it's possible, but you can of course not expect that the gradients are close to each other. Because I can start from a map which is basically constant, and I can approximate it with the G, and the G has to have a large derivative, and this would have derivative 0. So I cannot really ask for a norm, density in a norm which controls the derivatives. Right? If I don't ask for a norm which controls the derivatives, of course the Lipschitz functions are perfectly a complete space just with respect to the pointwise topology even. But if I don't ask for anything on the norm, then I cannot preserve the C1 property, the continuity of the norm. And the advantage of the case is we have really nice C1 solutions. And now the second question is the one I focus on. If n equals n, of course then the star becomes just that the derivative of f has to be in On, which is the union of the rotations. So there's the determinant equals 1, and SO minus n, which are isometries where the determinant equals minus 1. And if f is a C1 map, it follows that the determinant of df is constant locally. For instance, constant 1. And then by Liouville theorem, tells us that the whole gradient is constant. So we have no chance to approximate with such functions which are from the outset not affine or which are basically very small. Right? And the solution out of this is you relax the condition star. So look for f out of which are Lipschitz 1. So contractions, and now the derivative exists almost everywhere still. So the derivative of x has to be in On. Liouville result would hold even if you are not just for Lipschitz functions. So you have to use the full orthogonal group almost everywhere. And indeed, then you find many solutions. So there is the main work which I'm relying upon is by Da Coruña, Marcellini, and let's be a bit more precise. They basically said if you let's have omega in Rn, you take an F0 as a boundary datum which goes from omega into Rn and is strictly short. So the Lipschitz constant is less than 1 of F0 is less than 1. And now you look at the fact that the isometries in this weak sense are residual in the space of all Lipschitz functions, Lipschitz 1 functions von omega into R to the n, intersected with the functions that equal F0 on the boundary. So given the boundary datum, you find in all the possible spaces, of course there is at least one function which you can extend, but you have many. You find a set which is big in the topological sense, so the complement of the set is meager in this complete space. Just to make it clear once more, the norm we use is the L infinity norm. Right. And that's good news because we have many such functions. You can also establish this with the convex integration that you have many such functions. We have even residually many such functions, but the bad news is there exists an f from Rn into Rn, which is an isometry in the sense, and f is identically 0, or let's say on the space of all x, where the last coordinate is 0. So on this space, the function is 0, and it's a decent isometry behave on this side, but on this side, the derivative is of course not what it's supposed to be. So it collapses basically an n-1 dimensional space to a point. And so it's in no way an isometry in the sense the geometer wanted it to be. It doesn't preserve the length of curves. And that's why there was a complaint if there's the book by Gromov about partial differential inclusions, and he has some construction of functions which are isometry in the strong sense, and he basically asked if, well, the statement was transmitted to me basically from Cedric Villani in one or two more relays in the middle. So Gromov said somehow he doesn't believe that the cutting-free method is giving this nice function which he really wants, right? And that's what we actually want to discuss here. That is strong. Nevertheless, the isometries, length-preserving isometries, length of curves preserving functions are residual. And the method, one way or the other, you look at it, what is really done here, this construction, and also the the construction by Müller and Schwerak, is in some sense an approach which is coming from the calculus variation. So you define an energy function. It is expensive for your deformation to have the gradient not in the group of isometries, right? And this problem is non-convex. That's it makes it so funny and interesting for us. But you can essentially prove you are still able to solve this problem. You are still able to find a function of cost 0. In this case, even typically the functions of cost 0, which means that the gradient is almost everywhere in the set which you prescribe. But from the very outset, because you take a variational approach, you don't care about subsets of dimension less than let x 0. This is not in the scope of the method, essentially. So one has to look at the kind of slightly different ways to make the things work. Actually, taking this opportunity, I want to define classes of curve-preserving functions. There are actually 3. Once we answer the most simple case, we run into a paper by Petrunin, and we learn there are several functions. So let me give you 3 interesting classes. The first one in our metric space. What is the first? The F is an isometry. I just use naively the word which I used before. If the length of every curve for every gamma curve in X. So continuous curve was continuous. I didn't say continuous. The next one, it's a weak isometry. The same condition holds true for every gamma curve in X rectifiable. So the length of the curve itself should be finite. And then the F is called a strong isometry. The following is true for every x and y. The distance from x to y is the same as the lim. Epsilon goes to 0. And now I call it L hat of F composed with C. Sorry. Infinimum. So it's the length of a chain which I'm looking at here. The epsilon and the C has to be an epsilon fine chain connecting x to y, which means just that x0 equals x, xk equals y, and of course the distance from xj plus 1 is always less than epsilon. And the length is just the same expression which I used here. So the sum of the distances fxi plus 1 is the length of the chain. Well, and I said we struggled first with answering this question just for this. Actually, everything we thought about was weak isometries. Then we were bumping into this Petrunin paper, and the first question came up: are these 3 classes are they different, or what's the question at all about this? And I want to give you this nice example, which shows that this To some extent they are different. No. You go up again.
You stop it by right.
What? So back. So an example is actually a very convincing one. You take K to be the von Koch curve. In R2. And by the results I will briefly mention, there exists an F with the following property. F is identically 0 on K, and F is a strong isometry in each ball B, which is in R2 minus the von Koch curve. Right, so basically, what I said before, on the boundary you need a small function which doesn't change too much, so being 0 is the best you can hope for. And now you are able to do this. Then what follows? Then it follows that F is a weak isometry but not an isometry. Of course, the von Koch curve itself, I can take it as a gamma, and then I see that the length of F composed with gamma is 0, which is less than infinity, the length of K. And of course, if the length of gamma is finite, then this is essentially the length of gamma minus K. So now we have countably many pieces because the von Koch curve is doesn't contain a rectifiable piece, so every curve has the length outside there, and this is then mapped to, because these things can be covered by the balls where we are, so this is the length of F composed with gamma. So the infinitely long curves make the trouble. Of course, only those which do not contain subcurves of finite length. But this was very, very strange for us. And on the same theme, it's actually true that F, if you restrict it now to R2 minus K, is an isometry. Because of this property, whenever you take a curve, okay, you can basically, it's a compact image in this complement and you work your way through, but not a strong isometry. For the very same reason, you can work it out yourself. Essentially, if this is the von Koch curve, you take 2 points which are very close to the von Koch curve, and now you essentially, for any epsilon, you can choose an epsilon chain here, finite epsilon chain, and you move the points of this epsilon chain, the fixed number of points of the epsilon chain, just as little as you wish inside the complement of K. So So you have a finite number of points, maybe 10 million. You move it just a little bit into the set. You produce a chain of the length of the image is just a million times the delta, which you have chosen because you moved just a little bit. So you produce chains which are arbitrarily short inside the set, but because the chains are not all a priori bound in one curve, you do not get a contradiction if you go to the limit, right? So essentially you will find chains such that the lambda, this limit here, is the sum of the two distances of the point to the Van Gogh curve, because you need a little bit to connect here, but it's much less than what you need to connect along the Van Gogh curve. So that's basically a modification of something which just Petrunin did in the general metric setting. He asked the question, if f is in V1 closed 0 of Rn into Rn, an isometry, does it follow that's a strong isometry? And don't ask him about this question, because the first thing we did wrong was that we used the wrong term. We used the Gromov terminology, which he complained about. Ask him about path isometries if you meet him. But that's the question, right? And you see the difference, the thing is closed this time, so I cannot make this trick that I can go simply outside with my curve. He has an example in metric spaces. It's possible to do this counterexample. The so-called thing pseudo-arc, which is worse than the Van Gogh curve. It's a continuum, and every curve which you choose inside infinite or finite lengths has to leave the curve very often. Every curve you choose has to leave the continuum very often. But I was not able to do anything like this in the plane. Right. So these are the three classes which are all different, and now let me just tell briefly what you obtain. Then you look at typical functions. Basically, two kinds of statements. The one says if I take any boundary datum, so I take a set K in R to the n compact, then I take a G which goes from K into R to the n and is short. So one Lipschitz. Then the set of those F which are one Lipschitz on Rn, F on K is G. Then in space, again an infinity norm, is the set of F such that for every ball, or let's say M, compact, convex, M in Rn minus something I have to tell you in a moment what it is, the unique extension hall, such that the F is in any such set a strong isometry. It is a residual set. So the complement of the set is meager. What is this set? I can give you a very easy definition. It's the union of convex halves of all H, where H is a subset of the domain of K, and G on the H is a fine isometry. It's really a global isometry, not just in the weak sense, but in the strict sense. And it's also the same as the set of those X, such that there exists the point P of X, such that every extension, the one extension, f in X is P of X. So there might be some points outside of the set where the extension is uniquely determined, and there you have no chance to do anything. So the classical example is K is the union of the unit square, the boundary of the unit square, and f of xy is x0. Of course, you find out f of xy is also xy on 0, 1 squared for every extension, because the function is from here to here, it's one Lipschitz, so it has to be linear on this ray, and because it's trivial in the second coordinate, you can never find an isometric extension, right? It's basically, it's much too small. So there must be something about the set. You have to avoid the set. If you avoid it, then you have the property that the typical extension does what you want. And now you might also ask, so what happens if I don't fix the function in at once? And that's the last statement. If just the kf is given, and it's compact, then we can put it like this: the set of f restricted to K, F strong isometry in Rn. This set, take all the restrictions to K, is residual in the one Lipschitz functions from K into Rn. So if I take a typical function, basically the set C, K we are interested in might be very complicated. You don't have curves or anything in the set. It's this continuum. I don't know what is this definition really meaning, that it preserves length of curves if it's a straight discontinuum. The strongest property you could hope for is simply that it's the restriction of something which does the thing on the whole space, right? So if you choose this correctly, then of course also the strange example I've shown, just making it tight along the vertical segment will not show up. And so the typical one Lipschitz map on any continuum, on any compact set is basically a strong isometry. And now the annoying part of the story is we are able to extend Ra also in the Riemannian setting. And we do have a problem because we have no special technology for part B, so we should prove it for part C, which we can handle in the Euclidean case. But there are a couple of statements which would be useful in the book of Gromov if we were able to verify them. So at the moment we don't know what is the situation for Riemannian manifolds with the same property of residuality of this maps holds there. Okay, I think that's all I want to say.